as you read the other day for kind of a preview of this chapter, this is all about energy. And in terms of energy, there's a couple different ways we can define or describe energy. One is the ability to do work. And I always kind of refer to that as more of a physics type definition of energy as opposed to a chemistry type. So if you take physics, you'll look at energy in terms of an object's ability to do work. We'll look at it more in the definition of an object's ability to produce heat. Okay, so that's our main focus, but they're the same thing. Work and heat are basically just two different ways of looking. Oh, what did I do? Where did it go? There we go. And just like we've seen back from the beginning of the year, we've said we have to obey the law of conservation of matter, obey the law of conservation of mass. We also have to obey the law of conservation of energy, in the fact that we cannot create or destroy heat. Okay, we are just transferring heat or energy. When I say energy or heat, we're using those terms synonymously. So we are transferring heat or energy from one substance to another. We are not creating or destroying it. And one of those ways that heat can be transferred is between either kinetic or potential energy. Potential energy represents energy that is stored. Okay, you're not using it, it's just there for if you need it, you've got it, but you're not doing anything with it. Yeah.
If it can be stored, does energy have like a mass? Can it have a mass?
It does not have a mass. It has energy units, which we'll get into that more in a little bit. And this potential energy, how much a substance potential energy is all based on how the elements are put together, the arrangements of them in a compound. So certain elements or compounds have different amounts of potential or stored energy. Again, we'll get into values more as we go through the notes. Whereas kinetic energy is the energy of motion. So you can take that potential energy and convert it into kinetic energy when you're getting ready to do something. Okay, so anything with kinematics, kinesthetics, kinesiology means movement or motion. And we'll get into that more. Also, we'll talk a lot more about kinetics second semester, but that is the energy of motion. And so the kinetic energy is based on its state of matter. And as we change the state of matter, the substance will have differing amounts of energy because, again, kinetic energy is based on motion. And as we'll get into in our gas unit next semester, different states of matter have different relative amounts of motion. And the other thing that is related to kinetic energy is the temperature of the substance. Now, heat and temperature are not the same thing, but the temperature is proportional to its kinetic energy. So they're not the same thing. Heat and temperature aren't the same thing, but they are related to each other. So as we increase the kinetic energy of a substance, we also increase the temperature, or by increasing the temperature, we can increase the kinetic energy of a substance. So as one goes up, the other one goes up. As one goes down, the other goes down. Again, we'll get into looking at changing the different states of matter here in a couple slides. So in section 1 of chapter 15, it gets into heat. And again, like I said on the previous slide, heat and energy are interchangeable terms. Temperature and heat are not. Okay, so we can interchange temperature with energy, but we cannot interchange temperature with heat. They're related, but they're not the same thing. And one of the things that shows they're not the same thing is we have a totally different unit for heat, and that is the letter, that's a Q. That's a lowercase q. Usually we can use uppercase Q's also. And heat will spontaneously move or flow from hotter objects to colder objects. Just like the heat coming out of the radiator or whatever that thing is over there, the hot air will spread out and flow to colder areas and ultimately warm up those areas. So heat will just naturally flow from warmer to colder objects. And again, we're not creating or destroying energy or heat, we're just rearranging it. So as the warmer object loses heat, that heat just doesn't disappear, something has to absorb that heat. So when something is losing or releasing heat, the temperature will decrease because it's getting colder, but then some other object has to gain or absorb that heat. And so that temperature gets warmer. So the warmer object will release heat and its temperature gets colder, where the colder object will absorb that heat and its temperature will increase. So the symbol we use for heat is a Q, and usually we use a capital Q. I don't know why there's a lowercase q there. But the units that we use, as you saw on your homework, there's actually a couple different units we can use for heat. And one of those is the calorie, which we abbreviate CAL. And what the unit calorie is based upon is how much heat it takes to raise 1 gram of water by 1 degree Celsius. So that's literally what the unit, one single calorie, is based on, is how much energy does it take to make 1 gram of water or 1 milliliter of water increase by a temperature of 1 degree Celsius. And it's a metric unit, so we can have regular calories, that's our base unit. We can have millicalories, nanocalories, and we can even have kilocalories, which is what your food calories are. So if you look at a food label on something you're eating or drinking, it'll have how many calories are in a serving. That's a capital C calorie, and that actually represents a kilocalorie. So it's 1,000 times larger than just a regular calorie of our base unit. I don't know why they do that. My guess is they don't want to freak Americans out into thinking that we're using metrics, so they just call it a calorie instead of kilocalorie. But food calories are actually in kilocalories, are 1,000 times larger. The other unit that we can use for heat or energy is the joule, Joule. And the symbol we use for that is a capital J. And that too is a base unit, and it's also metric. So we can have millijoules, nanojoules, kilojoules. So we can move that just like we do the gram, the meter, the liter. We can move calories and joules around the metric scale however we want. Now the joule, though, is a little different in terms of its magnitude. So if we want to convert between calories and joules, 1 calorie is equal to 4.18 joules. Okay, so if we have something in calories, but we wanna convert it to joules, we would multiply that value by 4.18. Or if we're in joules and we wanna convert to calories, we flip that around and divide by 4.18. Okay, so they're measuring the same thing, they're just different units that we measure them with. So you will have to be able to convert both of these across any units of the metric system, or convert between calories and joules, yeah.
Will the difference between calories and joules be on our?
That's a good question, I can't remember if it is or not. No, it is not. So, yeah, so you just have to know the 4.18. Okay, and then what you were doing on the problems from the book, bless you, last night, where you were using heat to calculate or find specific heat, which we represent with the letter C. And what specific heat represents is the amount of heat required to raise 1 gram of any substance by 1 degree Celsius. Okay, now up here we define the calorie by how much energy it took to raise 1 gram of water by 1 degree Celsius. Okay, so it's the same concept, it's just this is for any substance. So every substance has its own unique specific heat of how much energy it takes to increase 1 gram of that by 1 degree Celsius. So that's why it's called specific heat. It's specific to a substance. And that's actually, because it's specific to the substance, we can use that to identify different substances. Just like we did with density way back in the beginning of the year. Each substance has its own unique density, and we could once we calculated the density, we could figure out what substance it is. Same is true for specific heat. So we can take, and we'll get into how we figure that out here in just a little bit. But once we figure out the specific heat, we can look it up on a table, like over here. Here's a handful of different substances' specific heats, and we can identify the substance based on that. And you can see there's all different values, like water. Now, you gotta pay attention to the units, and we'll talk more about the units on specific heat. In this table in the notes, the units for the specific heat is joules per gram degree Celsius, and we'll take a look at why that's so here in a little bit. But if you notice, water is 4.18 or 4.184. And then some other substances like silver up at the top is just 0.235. So the size of the specific heat can tell you a lot about the substance. In the case of water, water's very big compared to these other substances there. You know, water's over 4 times larger than one is 4.184 compared to silver of just 0.235. What that tells us is that water needs a lot of energy to raise its temperature. Whereas silver and copper, all the metals on there, aluminum, iron, they all have specific heats less than 1, very tiny amounts. So that means it doesn't take a lot of energy or heat to change their temperatures. And if you've ever, been in a swimming pool right in the beginning, very start of the summer, right after it got filled, what's the water feel like?
Still pretty cold.
It's pretty cold, yeah, because even if it has a heater, it's gonna take a long time for that water to warm up. Where same area, you go and sit on a metal bench on a hot sunny day, what's that metal bench gonna feel like?
A lot hotter.
It's gonna feel pretty hot, yeah. So metals, because they have a small specific heat, they heat up and cool down very quickly. Where substances that have larger specific heats like water, it takes a lot more time because it's gotta absorb a lot more energy to change their temperature. So yeah, I guess I can put that up there. So comparing water versus any metal, I put iron up there, but any metal. So, if we know the specific heat of a substance, and again, the units are joules per gram degree Celsius, and we have how much of that substance and what temperature changes, we can figure out how much energy it's either going to absorb if it's gonna get warmer, or release if it's gonna get colder. So we can plug that into this equation here where we're using a capital Q, which is really what it should be. So Q equals Cm delta T, where Q is our specific, is our heat. And that can either be in joules or calories, whichever unit you want. Where C is our specific heat. And the units on that, like on the table, can be joules per gram degree Celsius, or it can be calories per gram degree Celsius. And then M is mass, which for mass, we want that in grams, because we've got grams here in either one of our specific heat units. And then delta T represents the change in temperature, which that needs to be in degrees Celsius. And this equation, let me double check. Yes, this equation is on here. It's just, it has a S instead of a C for specific heat, but this is on your sheets. Okay, so you don't have to memorize
Wait,
that.
what, like, unit is this specific heat in? I can't see.
Either joules per gram degree Celsius, like it shows up there, or calories per gram degree Celsius.
So,
Wait,
Okay? So, as long as we know 3 of these things, we can solve for the 4th variable. Yep.
Would you only use calories if you were working with water?
No, you can, so these also have calorie values. Everything has joules or calories, and that's one of the things I think in the lab, I think the data table for the lab we're gonna do next week has both specific heats listed. So you do wanna be careful and make sure that you're matching up so that if your heat is in joules, you wanna make sure you're using the specific heat that is in joules per gram degree Celsius. Or if your heat is in calories, then you wanna use the specific heat that's in calories per gram degree Celsius. So yeah, you've gotta make sure your units are matching, and I think the lab data table gives you both units. So in the case of this example, it says if the temperature of 34.4 grams of ethanol increases from 25 degrees Celsius to 78.8 degrees Celsius, how much heat was absorbed? Now, it doesn't give us whether we want it in joules or calories. So in that case, as long as we label our answer, it doesn't really matter. But up here in this data table, the ethanol specific heat, again, is in joules per gram degree Celsius. So if we use that number, that's gonna give us our heat in joules. So all we have to do is take the specific heat from that table, 2.42. And again, you don't have to label your work with units, but I strongly recommend it. So that was joules per gram degree Celsius. And then we're gonna multiply by its mass in grams, 34.4 grams. And then our delta T. Okay, so again, that means change in temperature, so we need to subtract these two. And so, what is that? 53.8, right? And that's in degrees Celsius. So again, if you label your work, you can make sure you got it set up correctly, because this way our grams cancel, our degrees Celsius cancel, and that's gonna leave us with joules. And so when we plug that in, what do we come up with? So we have 2.42 times 34.4 times 53.8. So that gives us 4,470, and again, sig fig wise, as long as you're close, this number's been cut off. So the specific heats, those numbers go on and on. But we've got 3 here, so at least keep 3, if not 4. Don't give me 10, don't give me 1. So that would be 4,479 joules. Okay, now, the other part is, did we gain heat or lose heat?
Gain,
We gained heat, why?
because it's increasing
Because it
temperature.
increased the temperature, yeah, so this is how much heat was gained, because we increased the temperature. If the temperature went down by this amount, then we would have lost that heat, and we'll talk about how we indicate that here in a little bit.
You don't make the temperature a negative number if it's lost.
Well, you can, and that actually, if we're losing heat, technically then the value on this would be negative, okay?
You could also just put like that if it's lost.
Yeah. So the fact that we're increasing the temperature, we're absorbing heat, so this is a positive value. And yet, if we're decreasing the temperature, you could keep the negative here, and if you didn't, it's gonna be the same amount. It's just that in the end, you would make this a negative value to show that it was releasing energy. Do you have a question? No, okay. What else? Oh, yeah, and then the other thing, we're in joules. Say we wanted it in calories, but we didn't have the specific heat in calories. Once we get this answer, we can just convert it to calories by dividing by 4.18 joules. Okay, so just like we've done before with factor labeling, we can go back and forth by setting up a ratio. So if we wanted to see what that was in calories, that would be 1,071 calories. Okay? So the big thing is just making sure you've got the right unit, so whatever your specific heat is in, joules or calories, that's also gonna dictate what your heat value is. Okay, now what we'll be doing in the lab next week is what we call calorimetry. And now when they're figuring out the calories for the food and drinks you have that go on the labels, they use a fancy, what is called a bomb calorimeter. Obviously, we don't have one of those. We're just gonna use your basic coffee cup, styrofoam cup, to do calorimetry, because the styrofoam, the reason why they use styrofoam on coffee cups is it blocks the heat from either escaping and burning your hands and making the coffee cold or whatever. So we're just gonna use some styrofoam cups, but anything that is, whether it's a fancy food bomb calorimeter or a coffee cup calorimeter, what it does is it allows us to determine how much heat an object is either absorbing or releasing when we put it in this device. Now, of course, it's gonna be much more complicated when they, for figuring out food, but for our purposes, what we're gonna do is we'll go through this again when we get ready to do the lab next week, but we'll have some coffee cups, we'll put some water in it at room temperature, whatever the temperature of the water is coming out of the faucet, and then we're gonna heat up an object. In the case of the lab we're gonna do next week, we're gonna heat up a metal object and put it in the room temperature water. And again, remember, the heat flows from hot to cold. So that hot metal that we're gonna put in the cool water, it's gonna release its heat to the water. So the metal's temperature is gonna go down, the water's temperature is gonna go up. So yeah, I kinda got ahead of myself. And so once we figure that out, how much heat did what did the temperature of the metal do? What did the temperature of the water do? So the metal's temperature is gonna go down, the water's temperature is gonna go up. We can take that information to ultimately determine the specific heat of the metal, and then again, once we know what the specific heat of the metal is, we can identify the metal. Because again, we cannot create or destroy heat, so however much heat the metal lost is equal to the amount of heat the water gained. So this is basically what you're gonna be doing in the lab. You're just gonna be gathering the data on your own, yeah.
When you like have a hot like glass cup and you get it really cold, or it's really cold and it's really hot fast, is that like, and it like shatters, is that like related to energy
Yeah,
transfer?
it gains so much heat so quickly, it breaks the glass, yeah. And we'll talk more about that on the last slide after this one. I think that's the last slide, yeah. So, so this is kind of like the calculations you'll be doing for the lab next week. It's just you're gonna be figuring out your data to plug in. So here we have the initial temperature of water, and we have 125 grams of water in the coffee cup calorimeter, so the water in there, and we measure it, it's about 25.6 degrees Celsius. And then we heat it up 50 grams of some unknown metal, all the way up to 115 degrees Celsius. And then we put that hot metal into that 25.6 degrees Celsius water. And then again, the hot metal releases heat, so its temperature is going down. The cold water gains that heat, so its temperature goes up, and eventually they both end up at a temperature of 29.3 degrees Celsius. So ultimately, we're figuring out what the specific heat of the metal is, and then again, once we know what its specific heat is, we can calculate, we can identify what it is. So what we have to do first is, with the metal, we've got two variables. We don't know its specific heat, and we don't know right now the heat that it lost. So what we're gonna do first is we're gonna figure out how much heat did the water gain. So we're gonna figure out the heat of the water by plugging in the water specific heat, and again, we'll just use the 4.18 for water, but we could use the 1 calorie. In that case, we'd get heat in calories, but I'll use the 4.18. And then our mass of our water is 125 grams. And then the water's delta T, it went from 25.6 degrees Celsius up to 29.3. So what is that? 3.7 degrees Celsius, is that right?
Yeah.
3.7? Yep. And keep your sig figs here. These temperatures go out to the 100ths. So that's the delta T of our water. It started out at 25.6 and went up to 29.3. So then when we multiply all that together, and again, this has been cut off on the table, it even goes out another sig fig. So again, look at your ones that you actually measured. So we got 3 sig figs in both of those. So I'm gonna keep an extra one because we're not done yet. We're gonna use this value. So that gives us the heat that the water gained, 1,933 joules. Okay, so that's our heat that our water gained, that's a J. But remember, we cannot create or destroy heat. So this heat came from somewhere, and it came from the metal. So that is equal to Q that the metal lost. So now that we know how much heat the metal lost, we can rearrange this equation to solve for the specific heat of the metal. So when we do that, to solve for the specific heat of the metal, we're gonna take Q and divide it by, the mass times the delta T. Okay, so our Q again is the same, 1933 joules, Now, for the mass and the delta T, this is where we're gonna use the metal. We're now dealing with the metal, not the water. So the metal's mass, where to go, is 50 grams. And the delta T of the metal went from 115 down to 29.3. And that is 85.7. Now, we don't, in this case, we really don't care about signs. So you can subtract it any way you want. We're just looking at, we're here in this case, we could make this a negative number and then it would be positive. But specific heats are always positive. So again, this is all the metals information. And then we just plug it in. So we take 1933 divided by 50 and divide again by 85.7. And that gives us a specific heat of 0.451. And the units on that, notice none of these units cancel. That's how we get the joules per gram degrees Celsius. So that's our specific heat, and then we can go back to that table and look at that table. I'm not gonna switch back because then that's gonna take away all this stuff. And that is iron. So that tells us that our mystery metal is iron. And so that's exactly what you'll be doing for the lab next week. And again, we'll go over all of that again next week for the lab. Now, as Alice was asking before, do we need to make something negative or positive? That's where endothermic versus exothermic comes in. I can't remember if we mentioned this before. No? Okay. So, endothermic is a process where something absorbs heat from its surroundings, so it gets warmer. And that is actually what happens when ice melts. The whole reason why you put ice cubes in your drink, you're cooling your drink by the ice absorbing the heat from the drink. Okay, so when you put these really cold ice cubes in your drink, they start to melt. They melt because they're taking heat away from the drink to make your drink cooler. And the coolest your drink will get is the moment all the ice is gone. So as soon as all the ice has melted, that's the coldest temperature your drink will get, because then after that, it's going to just start absorbing heat from the outside and start getting warmer again. So something that is absorbing heat, we represent that with a positive Q. So like right here, this is actually a positive Q because it absorbed heat. The water got warmer. So it's a positive value. Where an exothermic process is an object that releases. Exo means out. Okay, endo means within, but that's a process that releases heat. And so as it releases heat, it's getting the surroundings, it's giving off heat to its surroundings. The object itself gets colder as it gives off heat and warms up the surroundings. And that's how, like, hand warmers, if you're gonna go to a football game outside this weekend, you might want some hand warmers. That's what you do when you twist them. It creates an exothermic chemical reaction that gives off heat and helps your hands stay warm. And so in that case, we represent that, because we're releasing heat, we represent that with negative value. So even though these are the same number, the same quantity, the metal lost heat, that is actually a negative 1933 joules. So it's negative because it's exothermic and it lost heat. Okay. So if it's a positive value, that means it's absorbing heat and getting warmer. If it's a negative value, that means it's releasing heat and getting colder. And then finally, our last slide for today is, earlier I mentioned kinetic energy is changes as we change the state of matter, and like we were talking about on the previous slide, ice cubes melting, they're going from a solid to a liquid, they're releasing, they're absorbing heat. So that's what happens. In order to get from one state of matter to the next, we have to either absorb energy or release energy, depending on which direction we're looking at. So as a substance changes its state of matter, it does so by either absorbing or releasing energy. So, one term called the molar heat, or enthalpy is the fancy name for heat of vaporization. So something vaporizing is going from a liquid to a gas. That is how much energy does it take to take, and don't worry about 1 mole, we're gonna talk about that when we come back from Christmas break, what moles are. But that's how much energy it takes to make a liquid become a gas. So to go from liquid state to the gaseous state, that is referred to as the heat of vaporization. And so in order to do that, something has to absorb heat. So the liquid has to absorb heat. Just like with water, if you're heating up water on the stove and it starts to boil, it's going from a liquid to a gas because it's absorbed heat from your burner on your stove. So that is an endothermic process. And like we talked about earlier, that means delta H, or enthalpy, sorry. Enthalpy is we use the letter H. So heat, or enthalpy, again, is the fancy name. That can be represented with the letter H. So again, if it's positive, so if delta H is positive, that means it's an endothermic. It's absorbing heat. It goes in these cycles, like I won't get it for a month and then I'll get it like multiple times a day. It's driving me nuts. Okay, so the delta H, just like earlier Q, would be positive for endothermic reactions. Where the opposite, so if we're going from a gas to a liquid, if we're gonna condense that water, or whatever it is, it doesn't have to be water, but if we're gonna go from a gas to a liquid, it's the same amount of heat, it's just now instead of absorbing heat, it's releasing heat. So for something, gas to condense into a liquid, it's going to release heat and be exothermic. So if delta H is negative, that means it's going to be exothermic. So again, endothermic if we're going from a liquid to a gas, and then vice versa, if we're going from a gas to a liquid, we need to release heat, and that will be a negative value. Then what's referred to as the molar heat, or enthalpy of fusion, that's just a fancy name for the heat required to melt 1 mole of, again, any substance, could be water or anything, into a liquid. So basically, we're melting something. So fusion, heat of fusion is is what we call melting. So like I was talking about with the ice cubes earlier, the ice cubes go from a solid to a liquid as they melt, and they cool your drink because they're absorbing, they're able to melt from the, whatever your drink is a warmer temperature, so they're absorbing that heat from your drink. And so the ice cubes temperature goes up, and that's why they melt while your drink's temperature goes down. So it's the same process as we're moving from a solid to a liquid. So solid to a liquid is also going to be endothermic. So again, delta H is a positive value. Where again, the opposite is true if we're going from a liquid and freezing it to a solid, like we've got out there with the snow. And at night, when it gets really cold, all the snow that melted during the daytime refreezes. That's an exothermic process where it's releasing heat and getting colder, so that's a negative value. So when we go from a liquid to a solid, that's going to be an exothermic process. And that's, I think all the farmers have already harvested their crops, but say we had an early freeze, I can't remember if we did this year or not. Farmers can actually spray their crops before the freeze with just a little bit of water, and that actually helps prevent the crops themselves from frost damage, because the water that's on the crops actually absorbs that heat as the temperatures go down. So you don't need to worry about that. But again, the ice cubes melting, or again freezing in the opposite direction, is probably the easy way. Now, what these curves do, let me draw one of these curves. These are called heating or cooling curves, depending on what direction we're gonna look at. So what happens is they go like this. Okay, we're across here, we're increasing energy. And here, so we're increasing energy as we go that way. And here we're increasing temperature. And so this region here, as you can see in the pink, this is the solid. And then this process here is melting. If we're increasing the heat, if we're going this way, if we're going that way, this is freezing. If we're decreasing energy. And then this value here is the liquid. And then here, this is boiling or vaporization, whatever you want to call it. Call it boiling. Going this way or condensing in this direction. And then this last little part is the gas phase. Okay, so you can see, to get to a gas, we have to increase the energy. And the interesting thing is here, in the case of water, where we're freezing, water only freezes at 0 degrees Celsius. So, or melts at 0 degrees Celsius. So, all we're doing when something is freezing or melting is we're increasing or decreasing its energy. The temperature doesn't change. And likewise up here, again, say we're at water, we're increasing or decreasing the energy to go from a liquid to a gas or a gas to a liquid, but the temperature stays the same. So that's why, again, temperature and energy are not technically the same thing. They're different, but the temperature remains constant while we're freezing, melting, or boiling, or condensing. All we're doing is changing the energy. Yeah.
Can you skip like from going to a liquid, like when you're burning wood? Could
Yes.
you like make it turn immediately into a gas?
And that's what this last up here, this top one is showing the same thing. Just ended. Yeah, the sublimation takes you directly from a solid to a gas. And that's where something like what James was asking about earlier, something, absorbs so much energy so quickly, it skips the liquid phase altogether, and goes directly, and same thing, we can go from a gas directly to a solid if we remove enough energy quickly enough. We can do that. Okay? Yeah.
If you have like a liquid that's